In this video, I'll be explaining how a mutation of a single base in the mRNA sequence, such as an addition or deletion, can lead to a dysfunctional mutated protein, possibly hindered by the development of a stop codon. I'm going to go through the process that it takes to deduce each codon, given the amino acids of both the mutant and the normal sequences. When given these two sequences, without even looking at the codons, you can see that there is a difference in amino acids. This is often caused by some sort of mutation within the sequence, hence why one is called the normal sequence and the other is called the mutated sequence. The difference starts on the third codon and continues on with the remaining codons that are given, which is not good for the protein's development. In the normal sequence, it can be seen that it continues past what we see, as implied by the 3 dots at the end. The mutant sequence doesn't have the dots and abruptly halts after 4 codons, which is often due to a stop codon, but we're not going to assume anything just yet. When determining what type of mutation occurred, it is smart to expand each codon into its 3 base pairs using this table. Some amino acids have many codons that code for that single amino acid, as shown, often differing in the 3rd base. In the first picture, the codons are displayed with the amino acid's variability in their 3rd base. When looking at that 3rd codon, its first base was mutated from uracil to adenine. When deciding between addition and substitution, we must look at the following bases and sometimes the next amino acid to find a pattern. When matching up the bases, the mutated sequence seems to be pushed to the right, which we hypothesize to be addition. We can then place the adenine base in the top sequence and push all the other bases into tertiary codons. From here we can start matching up the codons known with those that are unknown to get the correct sequence of bases, which allows us to confirm this hypothesis. With the 4 amino acids in the mutant correctly coded for, we can then look for a stop codon. The 3 stop codons are UGA, UAA, and UAG. In the 5th expected amino acid for the mutated sequence, we can see that the first base is unknown, but the 2nd and 3rd are both adenines. For there to be a stop codon, the first base must be uracil, which we can safely assume it is. We can then take the added adenine base and revert the sequence back to the normal one to deduce its codons. We're not able to determine the last 2 due to a lack of information. The mutated protein is dysfunctional because it is too short to complete its intended function. And here we have the normal and mutant sequences.